the very beginning to the very end. We will now be beginning with our speakers for the evening. We have five speakers today, which are the GDSC ML COCOM. They will be each taking a separate topic and taking you through the details of that particular topic. So, just as a reminder, this meeting will be recorded, and you will also be provided the materials so that you can refer to it later if you so feel to. Anybody having any doubts or anything can put it in the chat. We'll be able to read that. Unfortunately, we'll not be able to allow you to, open your microphone at this very time, but we'll be able to read the chat. So if you have anything, put it in the chat. So without further ado, I invite Janil Shah to begin with his presentation.
Okay, cool. So hello, hello. Yes, Smith, can you share the screen? Sorry for the inconvenience. I couldn't share my screen for some reason.
Just a moment, I'll share the screen. Is the screen visible?
Yeah, just scroll to the top. Okay, so let's start with the introduction to TensorFlow. So TensorFlow is a very helpful library to basically build neural networks. And to introduce it, we'll go with an example of a very simple neural network so that you understand how the syntax works and how TensorFlow really works. Okay. So for any first step, you need to start from the very basics of it, right? So that's why we're starting from a very simple neural network. And neural networks basically are a kind of machine learning models which basically help in optimizing or like figuring out a pattern in a question. So like if there's an input, the neural network gives an output to it. The output can be number of like x, y, z or only x. So for a basic function, let's just keep the function y equals 2 into x minus 1. Okay. So let that be our cost function, like the mapping from x to y. And let's start. So the imports, firstly, you need to download in TensorFlow. If you don't have it download, just simply pip install TensorFlow or like conda install TensorFlow. Anything works. You need TensorFlow, NumPy. These are the two important things, and obviously Python because you're doing with Python. So just go down, scroll down. We import TensorFlow, NumPy, and Keras. Keras is a module inside Tensor. Okay. So now, what is a neural network? Neural network, from the term itself, it's kind of like a neuron. A neuron, like a brain has neurons. Neurons is basically one node which perceives input and then it gives a signal, which is an output. Okay. The input can be of any size, the output can be of any size. The neuron will have some weights or some function inside of it, which changes the inputs and gives the correct output. Okay. Now, a very basic neural network is a one neuron neural network, and that is all is required for the function we're using. Okay. Now, to define a neuron, we basically go to the cell model equals tf.keras.sequential. So TF is the TensorFlow library, Keras is the module inside TensorFlow library, and sequential node is because we want the neural network to follow sequentially, but like it doesn't really matter because there's only one node here right now. Okay, and here we're defining it with keras.layers.dense, which is like a neural network definition, a neuron definition, and units equals one and input shape equals one. Units equals one meaning there is one neuron, and input shape equals one, meaning there's only one size of input because there is only one x and one y. Okay. Now, when you're compiling, you need to specify two things: a loss function and an optimization function. If you've studied basics of ML, you might know for like decision for like uh, linear regression, we have a loss function and an optimization function. The loss function in linear regression is simply loss like mean square error or like absolute square error, whatever you want. And optimization function is your gradient descent or something. And it's very similar here in neural networks. And here we need to just define the loss function and optimization. So like you can just read through the text. Uh, yeah, and now here we need to figure out the relation between y equals 2x minus 1, right? Computer needs to learn that y it is to 2x minus 1. Y equals 2 into x minus 1. Now, computer doesn't know the function. It needs to learn. So that's why we need to figure out a loss function to understand if the answer we're predicting is correct or not. And optimization function basically helps us reach the answer faster. Okay. Now, let's just provide the data because for every machine learning model, we need the data, right? And here I'm just defining the data manually. You're like in real world usage, the data is uh, provided in form of like data frames or like NumPy arrays. Here is just simple X to Y mapping. We can just declare it. So if you just, and here we just mentioned six random points where we map it. So like -1, if you put it in the function, you get -3 and so on. Okay. Till now, is it clear like what is a neural network and how we're like at least defining a simple neuron? Just give thumbs up if that's okay, cool. Now let's go to training the neural network. This is the part where we train and help the model understand the pattern behind the entire data. Okay. We simply call model.fit and give it x and y. Now, this is a very simple thing. We don't need to predefine the loss function or optimization function because it's very simple. But if you want, you can like define separately, which will be like shared later or in the later sessions of the code. Yeah, fitting is a very important step because this is where the model understands the intricacies behind the input and output. And in model.fit, you're given some parameters. The two parameters mentioned here, which are important, is x and y, because that is where we're training, and epochs. Now, epochs is a very common term in neural networks. Epochs is basically how many times the code will run and understand. Okay, because every single epoch, the code will make a guess, like this is my optimization function. This is my optimization function. Then this is my function. Then it checks with the error, like the loss function. and it learns on it, and it keeps on training till you reach 500, because that is the limit. You can go till 1000, but that is not required. If more epochs you do, more training time it takes. So there's always a parameter of like how many epochs you want to train with how much time you have, because this is a very simple model. The uh, more dense and more complicated models will take more times to run for each and every epoch. Okay, and now after you've trained it, you uh, fitting is basically training the model. After you train, you simply fit it with a new point. Okay, model.predict. Now you can give it any number of size of an array. If let's say because there's only one input here, you can give it 10 rows of inputs, and it'll give you 10 columns, 10 rows of outputs also, because it'll map for every single x, it'll give you an y. Okay. Now here we just give it a one input, and it'll give 19 if you look. Running ka time nahi hai, but this will give you 18.9999 something when you run it. And 18.999 is very close to 19, but it is not 19, right? If you look at the function we've defined, it is 2x minus 1. Should be pretty simple. 10 into 2 minus 1 is 19. But since we've only trained it on 6 data points, the the neural network learns on probabilities. And since it's probabilities and you're giving it only a small amount of data, it figured out that 18.9999 would be the best answer up to that point. Okay. Now, this is why we do never get 100% accurate answer. So keep that in mind. We try to keep it as close to possible, the answer. And yeah, so that is basic introduction to TensorFlows. Now, neural networks, this is very simple neural network, a one-layer neural network. Neural networks get complicated. There'll be many layers. Each layer has different nodes. Okay. And each node gives a different output. So like there can be many layers to it on many neural networks as well. So like 10 nodes and only one output, or like there'll be 10 nodes, 10 layers. There'll be 100 nodes. Every single thing doing different work, doing a different work. Now, how will you decide what node does what weights? Now, simply the fitting parameter, what it does is whatever output it gets. Like firstly, it gives random weights and you get a basic output. Now that output gets you understand okay, like if I'm getting 10 and the output should be 19, you have an error, right? The error with some maths behind it, that's it called back propagation, and with some maths, you basically update the weights of the neural network, and as you run the epochs, you go towards the better answer, and you get the accurate weights of every single node. Cool. Any doubts? You can like type it in chat or like just press thumbs up. Cool. So let's like I guess that's the end to introduction. Let's move on to the next topic, and it'll be done by Deep.
So let's continue on with the second part, which is gradient descent. Is my voice clear and video clear, and as well as the screen? Yes. Okay, so first of all, we will start with the loss functions. So loss function are basically like they try to give the difference between the actual thing and the thing which our model will be predicting. So here this is like the most simple loss function example, which is the mean squared error actually. So this y I had is basically like the predicted response. This will be predicted by our model. This yi is the actual response, and this is like the square. So, and here since we are doing 1 by n because it's a mean squared error. So this is the mean square error function. For simple linear regression model, if we say, then it's basically a constant plus slope into the variable, which is the basic function of linear regression. In that case, this loss function would look something like this, where yi hat is replaced by w0 plus w1 xi. So here we have to find the w0 and w1 values such that we need to minimize the mean squared error, because the thing is xi is basically our testing point and yi is our training point. So we can't change both of these. We just need to decide to w0 and w1 such that your mean squared error is least. So we'll now talk about gradients. For this purpose, we have gradients. So it's just that it's like really simple. It's just a matrix which holds all the partial derivatives. The gradient sign is a back triangle, reverse triangle. Some people call it as delta. And yeah, so gradient is basically with respect to once it's x, with respect to once it's y, and with respect to once it's z of this function f of x comma y comma z. And if x is the vector, then it's like basically x1, x2. So it's with respect to each and every component of the x. So if x is a vector which is like x1 plus x2 plus x3, then it's dou f by dou x1, dou f by dou x2, and up to this. So here, so basically, well, in simple terms, so a partial derivative, it's like, what does it do is that it maps the 3D R3 space to R, while the gradient, what is that it creates R spaces R3, it keeps the same amount of space. So R3 space remains R3 in case of a gradient. That's why it's more better than partial derivative. Here is one table which summarizes all of this. Yeah, and here is the notation warning. It is that we have to be aware of the notation. This is what it's trying to say. So here is the gradient intuition. So we will start with plotting sine xy. Uh, for every various values, we have plotted sine xy for every x and y values. So we can see that here for difference, here it's -1 and here it's +1. So like that sine has values within -1 and +1. So that's it. And so we are now trying to find gradient of sine xy. So this is here we have defined this. So grad f is like basically this is like this thing which is we have defined in Python. And here what is this gradient looks like. We'll get a better view of this in this picture. So here we have like sine xy and its gradient. So like the way it changes, this is what these arrows show. The larger these arrows are, the higher the plot has the gradients at that particular point. So yeah, and why it is the direction of like fastest increase. So here we can see that like say, although we can see here that x1 is like the highest partial derivative, we need to know that gradient is basically the best direction. Here partial derivative only considers one specific direction at a time, while gradient considers the overall direction at a time. And yeah, so say we are at position, say some random position x, and then we move like very small amount ahead, then this change from f from x to x plus v will be the partial derivatives of each and every component of the gradient. So like vi plus v1 v2, so that every I is 1 to d. So every single component, the partial derivative change into this V for every components. So in other words, in simple words, this change is actually just the dot product of del f dot v, which many of you have studied in the physics as well, in first year physics. And again, the dot product definition is a b mod a into mod v into cos theta. Now here, since del f and we have it as fixed. So basically, we need to maximize this cos theta, or we can say cos theta equals should be 1. That is, theta should be equals to 0. So that's why the gradient direction is the best way to best increase. Now we will be going to, for in case of gradient descent with one parameter. So basically gradient descent, as we have seen till now, it's just that the it helps us optimize your loss function more efficiently than like in the manual way, where you can just kind of instead of experimenting, we can more easily. It is like a more better method to optimize our loss functions and to reduce the mean squared error. Like mean squared is an example of a loss function. So again, we will start with our simple linear model WXI. So we are not considering the constant thing. So yeah, and so again, the mean squared error looks something like this. Now we will take the gradient, the partial derivative of this. Sorry, the complete derivative of this, and then let's try to calculate the gradient at loss for the slope as w 0.5. So w equals to 0.5. Now here we are adding one more hyperparameter, which is alpha. So I am not going to deep dive into hyperparameters because it's another whole topic. Just think of it as a constant which balances it out, right? So again, so this is how the equation looks at it. W nu is W minus alpha into 18. So in this way, we are going to keep on optimizing the W such that the mean squared error is the minimum. So and here is the pseudo code. So like we'll begin with some arbitrary value of W, which is like this. We will start with some arbitrary value, and then we'll calculate the mean gradient across all examples, update this, and we'll keep on repeating until and unless we'll reach the most optimal W, where the mean squared error is the least. So now it's the now we'll come to the next part, which is the building and training. Most of it was shown to you by Janil. It's very similar. Again, the function 2 into x minus 1 we have defined. We have the sequential we have the sequential class from the keras, which is again a part of the TensorFlow library, as you can see here. You will be having the input shape as a single, which is like a single thing as an input, since we don't have multiple columns for the input. Again, we'll compile this model, and for this we'll be using the stochastic gradient descent, which is again like which is similar to gradient descent only, and we will be using as loss function here as our mean squared error. So basically in this deep learning model, we have used gradient descent as our optimizer and mean squared error as our loss function. So this, the thing which I have shown you above, this thing is going to happen in the background, this whole maths. We'll be providing some data. Again, we are not going to make a data set and all this in this simple way. Can provide the data, and we're going to provide it such a way that 2x minus 1 is always satisfied. Again, we'll train and we'll run for 500 epochs, and then we'll print the prediction of the model. For here I have taken the 10 value. So again, it's 18.98 and not 19, because again, well, neural network deals with probabilities and not like real certainties or things like, okay, in case of neural network, it can happen and it cannot happen as well. But in case of real life, it's like it should happen. So 2x minus 1, we all know, like in for x equals to 10, it's 19. But since neural networks is working on probabilities, that's why it's giving it 18.9, because it's giving an approx probability and not certain thing. So that was it about neural networks training as well as the gradients. I will pass it on to Soham from now. Thank you. Any doubts, you can put it in the chat.
I hope you can see my screen. Yeah. Perfect. If a screen is visible, could you like have a thumbs up? Put a thumbs up. Okay, cool. Yeah. So I'll start with what exactly a neural network is. So okay, imagine you're trying to teach a computer to recognize images of koalas, right? You start by showing. Okay, is my screen visible? Sorry. I like if a thumbs up or something.
It's visible, sir.
Okay, perfect. Right. So, okay, imagine you're trying to teach a computer to recognize images of koalas, right? You start by showing it a picture of a koala and then ask it to learn what features are important for identifying a koala. So you gather a bunch of friends, each specializing in analyzing specific parts of the image. Like one of your friends just analyzes its eyes, the other one nose, and so on and so forth. The eyes, nose are called features, and analyzing these features is called as feature extraction. Now, for each feature, your friend assigns a weight, which represents how crucial that feature is in determining whether the image is a koala. These weights act like important scores. Higher the weight means the feature is more critical in the prediction. Now, your computer. So, let's say in this condition, when your friend sees an image of a lion's eyes, it would say that the weight assigned to it is zero, as your friend is sure that this isn't these aren't koala's eyes, right? If it sees a bear's eyes, it would be it is close to a koala but not exactly a koala. So this could be it. So that's the reason the weight assigned would be zero point 0.5. But once it sees the koala's eyes, it would be iska weight 1 hai. That means that these eyes are for koala. Uh, so now your computer uses these weighted features along with a bias, a term for accounting the overall errors, to calculate the image is likely to be a koala or not. So this process is similar to a simplified neuron in a neural network, combining inputs with weights and bias to produce an output, right? The formula for it is the weighted sum, as Janil said at the start. The weighted sum is equal to the weight into the feature. Let's say the weight of eyes is zero point 0.2, and so that's the reason. So face is equal to eyes into the weight, nose, that's the feature, into the weight, uh yeah, and plus the bias. Now, if the computer's prediction is incorrect, let's say I predict that this is a koala, the image is a koala, but it is not. So what it does, to it goes back, it back propagates, adjusts the weight and the bias, and then trains it again to check if the desired output image is the same as what we have predicted, right? So computer gradually learns how to recognize koalas and or how to recognize a particular feature or a particular whatever you want to predict, right? So this is what a neural network is. So this is how an architecture of a neural network looks like. You have an input layer where you input the image, which, let's say, if my image is of 500 pixels, it will input 500 pixels. Have a hidden layer. Your hidden layer signifies your features or feature extraction, where one layer would be like nose scale, the other would be ear scale, so on and so forth. And the output would be what the output is, like if it's a koala or not. Now, this is about neural networks. Okay, so imagine I have a picture which is of 920 into 1080 into 3. So 920 width, 920 pixels ka width, 1080 the height, and 3 over here is the RGB value. So based on this, it's quite difficult, for the computational power would be quite high if I want to have an input layer of 6 million neurons. I have to add a hidden layer. Let's say my hidden layer is of 4 million neurons, right? The weights in this condition would be 24 million. My computational power would be very high, and my time taken would also be quite high. So that's the reason we use a convolutional neural networks. We convolutionize the image at the start. Okay, now what do I mean by convolutionalize the image? Okay, imagine I have a picture or I have a number 9. I want to identify the number 9. I look at the number, my human brain thinks, oh, 9 has three main features. A 9 has a loop, a circular loop, there is a straight line, and there's a small diagonal line at the end, right? Now, these are called features. But now that's my brain how it works. Now, how can I make the computer recognize these features, right? So, what I do is I take this image of 9 where there are white squares, I say I assign the number -1, and where there are black squares, I assign the number 1. Now, this, if you can see, it forms a 9. Perfect. Then you take the for the only the loopy pattern. Okay, now let's understand the top part of the 9, which is the loopy pattern. We take this pattern, and taking this pattern or extracting this pattern is called a filter, right? We extract this filter from the number 9, and then we multiply this filter with the original image. Now I multiply this filter with this entire image. Now, if I multiply this filter with this bottom half, we get the number -0.33. It's basic matrix multiplication. You can use the NumPy library for this. You get this filter -0.33. So I multiply this matrix with this matrix over here. Then I move by 1. So moving by one cell is called stride. So stride of 1. I would say that I have a matrix with a stride of 1 to get something called as a feature map. Now, what exactly is a feature map? The feature map where my value is 1 signifies that my image has a loopy pattern. Now, how do I know this? If I multiply this matrix by this filter, in the middle part over here, you can see 1, 1, 1, 1, 1, and -1 is center. The same pattern is over here. And that's the reason the matrix multiplication would be 1, giving me knowing that there is a loopy pattern in my image. If there was, let's say my number was 8, right? 8 has two loops. Then there would be another one over here at the bottom because there are two loops. And this is a filter for a loop, right? So filters are nothing but a feature detectors. So filters are location invariant. That means that wherever these features are, they will be detected. Something like koalas, an eye detector filter for the koala's eyes. So as you can see, the koala's eyes are over here. The filter will detect and create a feature map for the eyes, saying that there's koala's eyes over here. Similarly, over here and over here, the eyes, right? So moving on, uh, we had three filters, right? We had a loopy pattern, a straight line, and a diagonal line at the end. So there was a three filter. So that's the reason we get three feature maps out of it. Okay. Uh, and then this feature maps are then flattened to form my input layer. Now you may ask that, oh, Soham, what's the difference between then why do we use a filter? Like at the end of the day, I'm gonna have 6 million neurons at the end because उससे थोड़ा ही तो कम हो रहा है. It's not a great deal that is decreasing. So that's the reason we use something called as pooling. Okay. uh, okay, before pooling we apply something called as an activation function. Now, what is an activation function? Okay, activation function tells the helps us to not have a linear change in data. So um, hmm, it ensures non-linearity in data. So okay, without an activation function, the neural network would be limited for linear transformation, right? So, yeah, imagine, okay, okay, fine. Imagine you're trying to solve a puzzle, but there are only straight lines. You're only allowed to use straight lines. And if I ask you to draw a circle with only straight lines, it's going to be difficult, right? So to train a neural network with only linear functions is difficult. That's the reason we use a curve functions or any kind of activation functions to have a in non-linear outputs. That's the reason we use over here we're using a ReLU function. What a ReLU function does is just simple. So negative values hai, it will convert it to 0, while the positive values it will keep the same. So you can see minus 0.11 tha, it would do it, make it to 0, and 0.11 is going to keep as the same thing. Okay. Now, why do we use pooling? Pooling is used to reduce the size of the matrix. Essentially, what pooling does is it selects the maximum value from each region. So if a feature map, let's say that this was your feature map, right? Pooling would select a 2 by 2 pooling with a stride of 1 would select would select the maximum number of this 2 by 2 matrix. Now 0, 1, 0, 0.11 mein the maximum number is 1. So it would take a 1, right? Similarly, 1, 0.11, 0 and 0 mein the max number is 1. So pooling layers reduces the spatial dimension of the feature map while preserving the important information. So pooling helps in reducing the computational complexity and focusing on the essential features. So that's the reason you use pooling. Now, after pooling, your neural network gets your input layers are minimized or it gets quite less. And then after that, you can use your normal neural networks and then start training the data on that. So over here, you can see you after pooling, you flatten the layers. Flattening is basically a एक matrix को you convert into a 1D array. That's what flattening is. Then you add the hidden layers, and then you can predict ki whatever you want to predict. So let's take a look at an example code. Over here, I have taken an example of a CIFAR dataset. CIFAR dataset is nothing but there are 10 classes which have 32 by 32 by 3 ka images. Okay, there's airplane, automobile, bird, so on and so forth. So we'll do the basic steps. We'll import TensorFlow. So all the deep learning libraries are already inbuilt in TensorFlow and Keras. So you can import TensorFlow as TF, import TensorFlow.keras, import dataset, the layers. Layers is nothing but as we showed you over here. These are the layers. All the hidden layers rahega, your convolutional layers, pooling. All of this is all present in the TensorFlow.keras layers. I'm importing matplotlib to just plot my images, and numpy for any mathematical array if you want to change or play with some arrays. Okay, so I'm importing my dataset as xtrain, ytrain, xtest, ytest. After that, I'm just checking the shape of my xtest. Xtest is nothing, so that's 10,000 data sets with 32 by 32 by 3. That's the size of my image, 32 height, 32 width, and RGB ke liye 3. My ytrain dot shape is 550,000. There are 50,000 data sets in ytrain. Now, my ytrain, if you can see closely, this is a 2D matrix, right? If you see, there are two blocks. That means that this is a 2D matrix. I'm converting my 2D matrix into a 2D array. I'm converting a 2D array into a 1D array by simply saying ytrain dot reshape -1. I'm converting the changing my ytrain, so I have to also change my ytest. Then I'm defining the classes. The classes I'm defining in the same order of the data set over here. So make sure that when you're defining classes, it should be in the same order, like airplane, automobile, bird. Yeah, yeah, be same order mein you have to define. I've made a small function which helps me to visualize the images, right? Now, if I show you plot sample, I've made a plot sample x, y, and index. So if I put index 0, so if you see index zero पे मेरा number क्या था 6. Now 6 over here, if you look at the data set, 6 over here would be a frog, which is 0, 1, 2, 3, 4, 5, 6. And as you can see, there's a frog over here. You can see the image of a frog. Similarly, if I put 1, the one in the ytrain array would be 9, which is the ninth class, which is 7, 8, 9, which is the truck. And so we get a truck. then I'm dividing by 255. I'm dividing x train and x test. Okay, x train would be an array. X train is an image, right? 32 by 32 by 3 का एक image है. Uh, it's basic an image is basically a matrix of RGB colors. So एक cell उसमें से would be between the value of 0 to 255 depending on what the color code is. I am converting that color code into a number between 0 and 1. So 0 और 1 के बीच में, so अगर मेरा white रहेगा तो it will be 255. तो if I divide by 255 तो मेरा 1 हो जाएगा, और अगर मेरा black रहेगा तो 0 by 255 मतलब 0 होगा. So all my colors would be between 0 and 1 now, because I'm dividing it by 255. Now I'm building my neural network. So what I'm going to show you is I'm going to build an artificial neural network as well as a convolutional neural network to show you which one, why is CNN better than ANN. Yeah. So okay, so you can see ANN mein, I'm doing layers.flatten. That means I'm converting my 3D matrix into a 1D array with the input shape of 32 cross 3. I'm adding a hidden layer as I showed you over here. This is the hidden layer I'm adding. This is a hidden layer. I'm adding of 3000 neurons in this condition. So if you see an hidden layer of 3000 neurons with the activation function of ReLU. Uh, I'm adding another hidden layer of 10,000 neurons with activation function of ReLU. And the 10 would be my output layer, and the output layer would be output layer should be what I'm predicting. I'm predicting 10 classes. That's the reason I have 10 in my output layer. Then I compile my output layer with an optimizer of SGD with a stochastic gradient descent. Optimizer basically reduces your loss function, which is sparse categorical cross entropy. Loss function, as Deep explained earlier, you know what a loss function is. And matrix मतलब क्या दिखना चाहिए when I'm calculating my when I'm running my epochs. So as Janil said, epochs is basically one complete cycle through an entire training data set during the training of a model. It's like going through a textbook from start to finish. तुमको जितना समझा, that's your accuracy, and then you go through it again, you understand more, your accuracy increases, right? That's exactly what is happening epoch में. So मेरा first epoch में accuracy 0.35 था. After my 5 epochs, my accuracy came out to be 0.49. As you can see, the time is very high. It's 184 seconds लगता है एक epoch complete करने में. Now, that's for an artificial neural network. If I build if I build a convolutional neural network, I have filter. Filter is basically मेरे कितने features है. I don't have to mention the features individually. I don't have to tell कि like eye है, nose है, क्या. I can just mention how many features I want. So you can play around with this number. So I just put 32. With the kernel size is whatever your filter was. Filter का matrix अपना 3 by 3 था. So I've just put 3 by 3 matrix. The activation function of ReLU and an input shape of 32 by 32 by 3. Similarly, then I've put max pooling, my pooling layer, which was the 2 by 2 matrix. I have added another convolutional layer with 64 features in it this time, an activation function of ReLU, and a pooling layer of 2 by 2. After that, I did the same I do in artificial neural network. So if you can see the architecture of my CNN, at the end, there is a ANN at the end. So if you see this part, this is what I'm doing over here. Flatten कर रहा हूँ मैं, then adding the layer, adding hidden layers and predicting the output. So that's what I'm doing over here. Adding hidden layers, which is 64, and predicting the output. And then my output layer has 10 because the 10 classes. Activation function would be softmax, and I compile my using my optimizer loss and matrix. So as you can see the difference, my accuracy increases drastically, which is 78% of the accuracy. With time is decreasing because 61 seconds में लगता था, and then ANN took 184 seconds. So that's why you prefer a CNN. That's the reason why CNN is better than ANNs. And yeah, that is what happens in CNN. And if I test my CNN on my test data set, the accuracy comes out to be 90%. If you can see 0.90. So now, yeah, my friend Akash would tell you about RNNs. Next.
Right. Before we move on to Akash, does anybody have any doubts? If you do have any doubts, you can freely put it in the chat. So the answer is depending on the type of activation function, do we decide what loss function to use or what loss to use is completely independent? Well, it sometimes depends on what operation you're trying to perform and what sort of optimization you want. So that is what the loss function will depend upon. And the activation usually depends upon what the specific architecture of your network is. So they are both dependent on the same thing, but between themselves, they are independent. All right, Akashram, you can proceed.
Uh, am I audible? And is my screen? Uh, yes, this.
Your screen is not yet visible, Akash.
Oh, my screen isn't visible. Uh, yes, I will just share it now. So, is it visible now?
It doesn't.
It isn't. Okay. So, I guess if any of the other presenters can share the screen, it would be helpful. I'm audible, right? Uh, am I audible?
Give me a second. I'll check.
Yeah, sure. So like before we go on to what is RNN, let's try to think of the need of our for RNNs. Like as we understood from Soham, CNNs are useful for images or like data that has spatial dimensions. So images have two spatial dimensions, right? Length and width. Uh, they also have channels, RGB, but they aren't technically spatial dimensions. The they are different ways to look at this image. Uh, but what your data has a time limit to it. They like whether uh, like we had rain day before yesterday. We had rain yesterday. We didn't have rain today. Will we have rain tomorrow? Like uh like for problems like these and though like uh, because it isn't thing to consider the dimension of time. So to overcome this problem, we use RNs. Um, so it's I can't see the notebook.
Is the screen share visible at all?
Uh, I can't say. No. So in the meantime, let's discuss what other applications there are for this language. NLP is very much dependent on the order of the data. Like if you jumble up the words, the sentences won't make any sense, right? But we won't be covering NLP today because it has some other concept that require a seminar of its own. We will be like today we a situation or a real world problem that we'll try to solve using RNS. Another example will be weather forecast, of course. As simple as like we had rain yesterday and today, will we have it tomorrow? Uh, there are multiple other features that go into it. Let's say temperature, humidity, and a whole lot of stuff. What else? We have uh, stock analysis. Yes, a lot of people in our college are into stocks and uh, like and that sort of thing. So stock analysis, if you're dealing with stocks, you most probably will be dealing with RNs or there are some advancements in those fields that uh, the base is R. Um, else? Time series analysis, yes, anything that requires time again. So what else? Smith, if anyone else can share, Soham, can you share?
Oh, yeah, I'm sharing the screen. I am.
And the screen is visible on my end.
Oh,
Akash, could you
is it
just try to rejoin the meeting?
visible?
All right. It appears that Akash is having some connectivity issues. We'll move on directly to the next presenter in line.
Yeah. I'm so sorry that some people did that. But am I at least audible? Like, how are you here?
Akash, your audio is still choppy. Will have you present
I'll
at the end of the
so
thing.
yeah, sure.
Dipti, you can go ahead. Aditya, you're visible. You can begin with your presentation. You're visible but not audible, Aditya. We sincerely apologize for the technical difficulties we're having right now. Please keep your patience. We'll be resuming in just a moment.
Can you see my notebook?
No, your screen share is not visible, but your camera and mic are working perfectly. Aditya, your screen share is still not visible.
Can you share my collab notebook?
All right, sure.
So the next topic is deployment and production, and we will also discuss about tensor board. So after training and testing our model, we deploy our model for production. Deployment in TensorFlow refers to making the trained model accessible for use. Deploying model handles real-world data for inference and decision making. So imagine a race car. Production is putting that race car on a racetrack, whereas deployment is how you get the car there. Both are crucial. Production let you use your model power, while deployment ensure it runs smoothly and efficiently for real world use. In an ideal situation, a model performs well during testing but faces challenges in production due to difference in environment and audience. To ensure smooth operation, a residential pipeline is necessary to quickly recover from any issue without impacting user experience. This highlights the importance of making model production ready. So let's just talk about deploying our model for production and what all thing we need to take care of. The first and the crucial thing is package your model properly for deployment. Avoid using Jupyter Notebook or Google Colab directly. Instead, pack your model for production environment. Once your model is been packed, host it in the cloud server. Maintain the server. It is essential to ensure scalability and availability, which can be achieved using auto scaling. Global availability is another critical factor. Your model should support regional languages and user bias for global accessibility. Additionally, security and low latency should be taken care of. And to facilitate user access, provide an API for seamless interaction with your model. Make sure the API is always available for user prediction. So the last point is model versioning. For example, you have to build any model, and you have built a model of image classification 5 years ago. It won't be able to predict the image on the current data. So updating your model to the latest version is important to maintain the accuracy and relevance. Ensure user always have an access to the latest version for a better experience. Uh, so here you can see a chart, and you can see model versioning is not the only part of machine learning. There are many more things to do. Deployment and serving is a major part. So before jumping into the code, I will discuss all the points that I will discuss the step for deployment. The first is we have to train and test our model. Then we have to save our model in the same model format. Then we have to serve our model to the TensorFlow serving. Uh, after after uh, After serving our model, we have, as an end user, we have to send the request API to the server for the prediction. Ensure all the images should be in JSON format, and further we have to check the same model in the server does the correct prediction. So Smith, can you scroll a bit? Smith.
Scrolled to the simple CNN with the TF model server, right?
Okay. So in the first cell, I'm just checking the version of the Python is Python 3. If it is not, so it will generate the error. So there is a syntax error. I think instead of writing is, there should be we should write an equal to sign. Can you change that? Uh, Recompile it.
It's compiling. Just one second.
Okay. So in the next block of code, we have installed the necessary dependency for running the TensorFlow and TensorFlow Keras in Colab environment. Especially it install a Gripsio library with the version 1.59.0. So Gripsio act as an interaction between the different components of machine learning. After that, so our very first step is to train and test our model. So I have imported all the necessary libraries. Can you scroll a bit? So after installing the necessary library, I have checked the version for TensorFlow we are using. Now our task is to train and test our model. So for training and the testing any model, we have to divide the model. We have to load our model. After loading the model, we have to divide it into test and train, and we have to train it by using any algorithm. So here we will train our model by using a simple CNN algorithm. I have used a image floating data set, which is commonly used and practiced data set. In this data set, there are about 70,000 images in 10 different categories. In 10 different categories. So, can you scroll a bit to standardizing and normalizing of the data set? So here in this code, so in this code we have loaded the fashion data set and scaled the pixel value to the range 0.0 to 1.0, reshape the image and print out the information about the data set. In short, we are preparing our data set for training. So in the next block, in the next block we will train our model. Smith, scroll a bit.
Yeah, to the train and evaluate, right? Scroll.
So yeah, here we have used a simple CNN algorithm. Our much focus, we will not focus much on how we are training the model because our main agenda is how to deploy the model. So at this code, we have deployed a conventional neural network using TensorFlow API on a fashion data set. The model consists of conventional layer followed by a flattening layer and a dense softmax layer. It is then compiled with an Adam optimizer, space categorical, cross-trophy loss function, and an accuracy matrix. The model is trained for a 5 epoch on a training data set. After training the model, its performance can be evaluated and the text accuracy is printed. So you can see accuracy for each epoch and the average test accuracy. So our model is been trained. Now the second step is to save our model in a save model format. So save model format is like we are saving our model in a directory. So
Yeah, I've scrolled. Is it visible?
yes. The code fetch the Keras session. This code fetch the Keras session and save the train model in a train model format necessary for TensorFlow serving. It defines the input and output tensor signature and save the model to a temporary directory. The directory part is also printed for the reference. You can see it in the output session. So and also you can see all the file is being stored in a .pb format. So .pb format is a protocol buffer format, and in TensorFlow this format is used to hold the model, or we can say to save the model. uh, next next cell please. Now we have saved our model and we will examine our save model by using save model CLI. We are just checking what all thing is been saved in our directory. So so you can see all the information about the model, the input and the output, and data set, the data type value. It tells a lot about our model. So that's it. So after this, saving our model, the next step is to, can you scroll a bit? Yes. So after saving our model, we have to serve our model. But before serving, we have to do all the necessary setup and import all the package source. So importing all the package source, there are two different methods. One is aptitude and one is uh, blo- Docker container. So we are using aptitude here because it is been supported by collab environment. So the code stipends add the TensorFlow serving distribution URI as a package source and add the TensorFlow serving public key to the list of trusted key. Then it's update the package list to include the TensorFlow model service server package. So after installing all the package, Smith, can you scroll?
You want me to scroll past the installation of TensorFlow 7?
Can you scroll a bit? You are not audible. Yes.
All right.
So इतना नहीं करना है.
All right, I've scrolled back.
Okay, so here you can see in this line, in the very first cell, the line sets the environment and represent the directory where the train model is saved. The bash scripted runs the TensorFlow model server in the background, serving the save model name fashion model from the directory specified by the variable. The server listens on the port number 8501 for the REST API request, and the command ensures that the server continues to run even after the current cell ends. The output and the error message are being redirected to the log file, that is serve.log. So in the last cell, we are printing the last 5 lines from the serve.log file to check there is any error. So you can see there is no error, but there are some of the warnings. We can ignore that warning. Uh, so our model has been served. Now it's time to send a request API as an end user or as a client. But before that, we will check our mod is our model able to predict any images and their class correctly. So in this code, we define a function to display an example image from the test dataset. It will randomly select an image from the test dataset, reshape it to original dimension, and display it along with the corresponding label. The title of this image includes the class name based on the label. So you can see it has correctly identified the class name, which is trouser. Uh, so now it's time to send a request API to the server. But before that, we should convert all the test images into the JSON format, because TensorFlow serving support JSON format. So this so the first block of code converts a set of test image into the JSON format suitable for making prediction using TensorFlow model server. It create a JSON object with two keys. One is signature name and another is instant. The signature name specifies the signature to the user prediction, and the instant contain the image data in the list format. The JSON object is printed and display the and you can in the output you can see the first and last 50 characters. So in the second block of code, we have send the request API, and the image we have to predict in a JSON format. So in the output, you can see the image has been correct. The image has been predicted correctly. So it is a single image. What if we have a batch of image? That means a multiple image at a time. So for that, we will use a for loop and check whether our model can predict it correctly. So in the last block of code, you can see there are three images and it predict all three images correctly. So yeah, this is all about deployment, and it is a very basic code for deployment. The
I'll share the TensorBoard PDF.
Yes, yes. Just a moment.
All right. Akash, have you joined? Are you in the meeting again?
Yes, I have. I'm.
All right. So do one thing, Akash. Join as voice only, and I'll share the screen. Is that all right?
Yeah, yeah.
Dipti, you can stop sharing your screen for now. Is the screen visible?
Yes. So I guess we had talked why RNNs, right? Why we use RNNs instead of TNNs. Like, was that part clear at least? Um, Smith or anyone, like, can you just put a thumbs up if that part was clear, or I'll repeat it?
That part was mostly clear. You can proceed with the notebook.
Okay. Yeah. So yes, we've seen why RNNs, right? In what type of problems we use RNNs. So for this today's workshop, we'll take a real world scenario. Imagine you're the regional manager at Dunder Mifflin Paper Company, uh, and your corporate wants you to fire one of your salespeople. So for the criteria that they have given you is expected profit, not how they have done in the past, but how you think they will do in the future. But obviously, you have to take an informed decision, right? So we will this workshop will try to make sure how you can do. So um, this I've just mounted Google put in the necessary packages. Instead of the dataset path here, you'll have to put in whatever path you've stored your data in. So as you can see, we in df.head, we can see the salespeople's names: Dwight Schrute, Jim Halpert, Phyllis Vance, and Stanley Hudson. And in we have data in 0, 1, 2, 3, 4. What is 0, 1, 2, 3, 4? They just timestamps. At time 0, Dwight Schrute made 70 units of profit. At time 1, 75. Here the units are arbitrary. They could mean units sold or profit in hundreds or something. So with this data, like if we can't give this to a traditional machine learning model or CNN because obviously this is time dependent. It is every data point depends on the previous data point. So what uh, before we do anything further, we'll have to process it so that we can work on it. How do we process it? So this prepare data function just takes all your data and all your steps. What are steps? Steps are basically how many points are you looking for before predicting the next output. So let's say your steps are 5. Okay, so what this will do is take all your points and like make it into a batch of 5, and the y values will contain the six. Let's say the first 5 are in x1, and your y1 will be the sixth element. Then your x2 will be 2 to 6, and your y will be seventh element, and so on. So here we have just printed x0 and y0. That is if you, for Dwight Schrute, right? So 70 to 95 will be the first data point that we'll be considering to predict 95. So this will act as your training data. Smith, can you scroll down? Yeah. So, okay, features and data points. What does that mean? So when we have it in an one-dimensional array, like 70, 75, 85, 60, 90, TensorFlow considers it as 5 features of one single data point. Let's say, what do I mean by that? Okay. Uh, in traditional machine learning algorithms, you will have x1, x2, x3, x4, and you'll predict y, right? Y1 or whatever. So that x1, x2, x3, x4 will be your features. So in let's say temperature, humidity, and rainfall are your features. And will is this climate suitable to play tennis is your output. So TensorFlow considers if you give them one single one-dimensional array, TensorFlow considers them as features for the same data point. We don't need that. We want 70, 75, 85 to be represented as a separate data point. So we just change the array into a two-dimensional array with 70, 75 in their arrays of their own. So this represents that we have 5 separate data points with one feature each. If we are now just doing a simple arming with one variable, if we had more variables, we'll add more like 70 comma 71 or whatever, and that would be a two featured multivariate time series analysis. Next we need to create the model. So the model again follows the same principle. We've seen it again and again. we have a sequential, which like allows you to like run your layer sequentially. Then can we move a little up here? Yeah. So simple R we use a layer of simple RNN. Simple RNN basically is like your it's a simple layer that has some units inside it. What are units? You can think of them as nodes in a regular neural network. So we also have an activation function value which adds non-linearity as explained by Soham. And we want to return the sequences. What does that mean? So after every instance, after every data point is processed, we want to return the output so that it goes into the prediction of the next output. So that way, we recursively use everything, every data point. Now, so this get simple RNN forecast function. What does it do? So we provided with X, we provided Y, X train and Y train, and the salesperson's name and steps and features. It basically fits your data for every single salesperson. It fits your data, predicts the next n outputs. Here we're taking 5 as the next n. So uh, the prediction loop is very important. So after every output is taken, we add it to the temporary array, which then goes into the prediction of the next array. So after, let's say, endpoint is predicted, we append that end the prediction to the temporary array, which then goes into the prediction of the n plus one data point. Yes, that's basically. Can we roll down? Like
I've scrolled.
salespeople.
Just wait.
Yeah. Uh, yeah. So we have these four salespeople, and we are just following the function that we wrote above for all 5 of them, and we're getting these data points. Ignore the warning for now. They aren't important. So if we see what the predictions are for the predictions of for white Shroot, we get these 5 values. That is, in the future, white Shroot is predicted to make these amounts of profits. So after that, like let's have it in a visual form, right? So we can plot these for every single person. So as you can read, is expecting him to like not give much again, not that great. May do. Okay. So based on these expected values, you can say, okay, so we are definitely not firing right shoot. We are either gonna go with these three. So that's how you do that. But there is one shortcoming of RNN. That is, like, if you see somewhere in Phyllis Vance, you can see there are trends, right? It's from 10 to 20, and again from 20 to 30. There are somewhat visible trends that we can see. RNNs, because we're just considering the last 5 data points here, RNNs uh, or forget what uh, LSTM. What are LSTMs? LSTMs are basically improved RNNs. They have an additional feature of memory, a long-term memory. So you have two kinds of memories here. A long-time memory that stores information about the events that happened way in the past, and a short-term memory that. Can we scroll down a little more? How do these work? So here's the memory and some hidden state. Hidden state basically is your like input and the past output. Those together go as your hedge. The memory C. So we first take X and we we decide how much of the long-term memory do we intend to forget now that X has come in. So, like, if they did really good in the past, but they have been doing really bad in the past couple of data points, we'll say, okay, like, uh, forget some of those past data, they might not be relevant. Then, in this input and memory gate, of a how much new context are we adding to the long-term memory? So memory, the data point that I'm currently working on will be past memory for the next data points, right? So we then decide how much of this context is to be added to the long-term memory. So then we add those in there. And for output of every cell, we consider the long-term memory as well as the short-term memory. We then like do an operation together, and then we get the output. So what are these circles and dots and pluses and tanh, sigma? Like we see a lot of variables, a lot of symbols, a lot of names. Um, these are nothing but activation functions. Sigmoid is your activation function that takes in one data point. It might be anywhere from minus one single data point into zero. That's basically what sigmoid does. It is not like I saw the comments. It is not doesn't take an array as input and give the best probability. Tanh is just sigmoid, but it basically it's very much similar to sigmoid. It puts the values in -1 and 1. This is a lot of theory that won't be covered in a 20-25 minute session. But it is like this is the basic. You can do the math on your own if you wish. We also provide you with the code LSTM. So it's for to deepen. That's it, right? Right. If there are any questions, you can just put them in the chat.
All right. So I assume that everybody who is present here is already in the WhatsApp group as well. So if you have any other doubts at any point in time regarding the session, or indeed anything about machine learning anyway, you feel free to drop some messages in that chat as well. And as an added benefit for you people, we have the entire GitHub repository of every single notebook that was used here. We'll be sharing that with you on the WhatsApp group as well, and I'll be momentarily sharing it here as well. So if there is nobody else that has a doubt, we'll, I think, call the session to close. Thank you so much for everybody who was present here. It was lovely interacting with you people. The doubts in the chat were very helpful as well. And we really love to see that everybody who was in the chat actively was also helping each other, even before we got a chance to answer the questions. That was lovely to see as well. Who all will get a certificate? We will look at the attendance in the teams itself. Everybody who was present for a majority of the session will get a certificate, most likely. Yeah. So I've shared the GitHub repository here as well. I'll put it on WhatsApp as well. Once again, thank you to everybody who was here. It was wonderful interacting with you. This was day 1 of Tech Nexus, a trek through TensorFlow. Join in tomorrow again for the app-based session. Thank you. Have a good day.